Hello everyone. Let's start with lecture 2. So it's lecture 2 of physics, first year. Last time we stopped at scientific notation and today we'll continue from there. We will be covering short topics. Those are not very important uh, for your entry test, but these are important as far as board exams are concerned. You'll see some MCQs from these chapter from these topics, uh, maybe 2 or 3 MCQs. So there are few rules for the or few conventions for units. So conventions for yeah, I'm sorry, convention for units. So let's look over those conventions. The first one is that whenever you are writing the full name of unit, then you don't need to make first letter capital. Um, but when it is named after the after some scientist, after the name of some scientist, then in that case, its subscript or its single or symbol name or single name should be capital. So we have example like we have newtons. Newton is a unit of force, and now this newton has n small, but when we represent it with the symbol, then it will have n which is large. So this combines the first two rules or first two conventions. The second convention is that you'll write that first letter capital, and if you are writing the whole unit, then it would be in lowercase letters. The third rule, uh, yeah, the third convention or third rule, which is this is very important. The table 1.4 is the backbone of unit conversion. I would say that before starting with next lecture, learn this table 1.4 by heart. Learn by heart. It will help you a lot. There are a lot of prefixes there like arto, femto, pico, nano. What does they represent? How they will affect the unit conversion and what are their symbols? These are very important and used back and forth in numerical problems or in different topics. So this third rule is regarding these prefixes. So it says that whenever you write the prefix before unit, then you don't need to give any space for that, right? So you'll keep it together. For example, when you write 1 into 10 raised to the power 3 meter in form of millimeters, then you'll write it as 1 millimeter, right? So 1 in 10 to the power minus 3 meter is equal to 1 millimeter. So you will keep them together. This is third rule. The fourth rule is when you are combining two units. So when you're combining two units, for example, you are combining Newton meter, then you write it as Newton meter, and this is one space. You'll keep them one space apart. This comes handy when you write papers or when you go to the research world. In that case, these things matter, but in your exams, this should not matter a lot. Then the fifth rule is that do not use prefixes twice. What does this mean? That means you cannot use one, you cannot say that 1 millimeter. This is wrong. You can say 1 millimeter, but you cannot say this. This is right, this is wrong. Another example is you cannot say 1 micrometer, yet you can say 1 micrometer. This is correct, this is wrong, right? So this was fifth rule or fifth convention. Convention is a better word. Then here comes the sixth one, and in sixth you can write the units in the form of scientific notation, and for that you need one non-zero decimal number. So for that, let's say um, uh, we have 5.0 into 10 raised to the power, let's say 4 centimeter, and now you want to express this in the form of meter, in the form of meters, and then it's better, instead of writing it in centimeters, it's better to write it like 5.0 into 10 raised to power 2 meters. Now you have reduced this power and you have replaced it with the with another unit. So it's better to use these units instead of writing it in the scientific notation. Then there is a seventh convention, which is the second last convention. And what does it say? So when you are applying power to some unit and it carries some prefix, then that power is applied to the whole unit, not just base unit, but to the prefix also. So let's say I have 1 kilometer square, right? So for converting it to the meters, then you'd say it's 1,000 meters square, or you'd say that it is 1 into 10 raised to the power 6 meters square, right? So you need to multiply it with the whole. The last eighth convention is that whenever you are doing some lab work, you are making some measurements, let's say you'll most often see in your practicals that you are measuring something with the vernier caliper, right? And let's say it has a least count in centimeters. So instead of converting it to meters, it's not good practice. Not good practice. It's not good practice, right? So most convenient units you should use there. Why? Because it will help you to keep away from the errors. And once you are done with your calculations, readings, then you can easily convert those back and forth into the units you need. So that was conventions. Let's now jump to another, not much important, but it has a good role. So topic 1.4. Topic 1.4, which is errors and uncertainties. So first, before starting the topic, let's see what is difference between error and uncertainties. Error is the difference. It's the difference between measured value and actual value, right? So you have a bar of 1 meter and you measure it to be 1.1 meter, So 0.1 meter, 0.1 meter is the error, right? This is measured and this is actual, right? But uncertainty is the reliability of the results. Reliability of the results. So unreliability, I would say, unreliability of the results. So a measurement which is more uncertain is more unreliable, right? Okay, with this, let's see from where the error term, what is the source of errors, right? What are various sources of errors or various types of errors? Sources, first discuss sources. There are three sources. One is when someone measures something with negligence, then it's the first kind of error that someone can occur, or first source that one can occur. The second is that either the apparatus is faulty, right? And the third one is that the method or the technique that you are using to measure is not good, is not precise, right? So these are three sources of errors, and from these three sources, the types of errors that come up new people across is one types. These are sources, and now let me write it bit down. So types of errors could be random, could be systematic. Okay. What is random? Random mean by chance. Okay. So you are measuring, let's say there is a student who measures the length of a bar and it's 1.1 meter. Another student measures a length which is let's say 1.08 meter. And another one student again measure this, then he comes across the length of 1.11 meter. So this is random error, this is by chance, right? So I would call it by chance. There is no remedy, no remedy for this error. And the second one is systematic error. Systematic error, right? So that systematic error comes from, let's say you are using an instrument that has some error in it. I would say error which is consistent. So let's say you are measuring something with scale, and that scale has an error of 0.2 meter, 0.2 meter error of instrument, right? And whatever the measurement you take, you'll have an error of 0.2 meter every measurement, with every measurement. So this is called systematic error, and there is a remedy. There is a remedy for this. You can do it by calibration, right? You can calibrate your instrument and then you can get rid of this error. So systematic error, I would say it's good in the sense that it can be cured. With this, we can now move to our third short topic, which is 1.5, and that is significant figures. So significant figures, what are significant figures? Significant is anything which is important. So we are discussing measurement. So anything which is important for the measurement, or any numbers which are important for the measurement, are called significant figures, right? So we'll see which figures are significant. So let's say I have a scale, right? I have this scale, right? So I can measure, let's say this length is centimeter, right? Or for understanding it easily, let's say it is in yeah, keep it in centimeter, keep it in centimeter. So it's centimeter. So the least value that I can measure accurately is centimeter. So 1 centimeter is equal to 0.01 meter, right? So let's say I measure a length of 0.011 meter, right? So these two digits after decimal place are accurately known because this scale is able to measure up to 0.1 centimeter, right? Accurately known. But this last digit, this one, not accurately known. Okay. So if it is not accurately known, then this is the first digit which is not accurately known. So the combination of all accurately digits known plus one one not accurately known will make significant figure. We sometimes call it reasonable estimate, because with all the known digits, well-known digits and accurately known digits, and with one doubtful digit, you have a reasonable estimate. That's why these are called significant figures, right? Now there are some rules that will help you to determine that which figure is significant and which is not, right? So all the digits 1 2 3 up to so on are significant, but for zeros there are rules and we need to follow those rules. And what are those? Let's zero is embedded in two numbers, between two numbers, those are significant, then this implies the zero is also significant, right? Between two significant numbers, zero is significant. What is the second rule? Let me do it lower. What is the second rule? So let's say you have a number 0.00 4, 6, 7. So see, zeros are to the left of this non-zero number. So if you have zeros, all the zeros to the left of non-zero numbers and there is no other non-zero number, then in that case, these are not significant. What is the third rule? Zeros to the right. It should be zeros to the right. So let's consider an example. 3.570. So all the numbers that are right to the decimal are significant. But keep in mind, in case if you are dealing with integers, then you should also take care of the unit in which the measurement is done. So let's say you have measured a mass of 8,000 kg, and then you have the least count of the instrument. Least, let me write it clearly. So least count of instrument is 1 kg, and then it has 4 significant numbers, right? But why I'm saying this? Let's say we'll keep the same example, and I have measured kg, 8,000 kg, but least count is 10 kg. Then these three are significant, right? Then we have three significant numbers, right? This will bring us to couple this thing with the scientific notation. So when we are measuring something and we are writing it in the form of the scientific notation, then let's say 8.70 10 to the power 4 kg, then these three numbers are significant, right? There are some quick rules. I don't want to spend much time on those, but you can read the book for that, and it's quite simple and easy. But keep one thing in mind, that if you are manipulating these different numbers, then for example, you are multiplying or dividing or adding anything, then the numbers answer your answer must not contain significant figures more than the least significant number. Let's say you have got three different numbers and you are adding them, and the one has got four significant figures, one has got five, and one has got six. So your answer must contain four significant, right? It must contain four significant numbers. So you should keep this thing in mind. This is important. one quick rule of rounding, and then we are done. Let's say you are measuring something and the significant figures are 4, and you have measured it like 43.75, or let's remove this 5 and keep it static. The static could be anything, and after static there is also something. So you need to cut your measurement till here, right? These are rounding rules and very important. So you want to cut your measurement till here, and you have got 5 digits, but you want to make these 4, right? So in fourth place, if you have, you can have either odd or even, right? At fifth place, if you have a number greater than 5, greater than 5, then irrespective of second last number, either it is even or odd, you will increase it, increase it by 1. If that last digit is less than 5, then keep the second last, keep second last as it is. If this last digit is 5, then increase second last by 1 if that second last digit is odd, but keep this second last digit as it is if it is even. Okay, so let me finish off this thing. So this is a table, this is second last, this is last, and so if second last is greater than 5, then increase. If second last is less than 5, then do not increase. If the second last is equal to 5, then even, do not increase. Odd, increase. That's it. So with this, we'll stop our lecture here, and we'll continue from the later on from the next topic. The starting topics are not that much interesting, and we do not have any practical examples to correlate with, but later on you will see that this physics course will become interesting, more and more interesting, and we will see many practical examples to relate with, and that will help us to remember the concepts. So like my channel, you can see the annotated notes in the description, and see you with the next lecture. Have a good day. Bye.